All right, let's talk about one of the most incredible pieces of tech in your computer. I'm talking about the graphics card. It's the engine behind those mind-blowing video games, and as we're seeing more and more, it's also the muscle behind the entire AI revolution.
So, just to really set the stage for how powerful these things are, I've got a question for you. Think about a top-of-the-line graphics card, really pushed to its limits, running a super demanding game. How many calculations do you think it's crunching through every single second?
Okay, get ready for this. The answer is 36 trillion. That's not a typo. 36 trillion calculations a second. That's the firepower you need to render something as complex and beautiful as, say, the world of Cyberpunk 2077. Right there on your screen, instantly. I mean, that number is it's almost meaningless. It's so big.
Let's try to put that into perspective. Imagine every single person on this planet, you, me, everyone, doing one calculation per second. To match what one of these cards is doing, you'd need the population of, wait for it, 4,400 Earths. It's just completely wild.
So that's the big question, right? How in the world does a single piece of hardware pull off this seemingly impossible feat? Well, the secret isn't just about being fast. It's about being smart. It all comes down to its very unique architecture.
Okay, to really get this, there's a perfect analogy. It's all about the difference between a computer's main brain, the CPU, and the graphics brain, the GPU. Think of your CPU, your main processor, like a jumbo jet. It's incredibly fast, super versatile, it can do all sorts of complex jobs really quickly. Now the GPU, that's more like a massive cargo ship. It's not necessarily the fastest thing on the water, but its whole purpose is to move an unbelievable amount of simple stuff all at the same time.
So let's pop the hood and actually see what makes a GPU this computational cargo ship. How is it physically built? It really all comes down to a single, incredibly complex chip. We're talking about a piece of silicon like the GA102 from NVIDIA. And get this, it's built from 28.3 times billion tiny switches called transistors. Just a mind-boggling feat of engineering.
But it's not just a big, messy pile of 28 billion transistors. It's actually organized with incredible precision, kind of like a city. At the highest level, you have these big neighborhoods called graphics processing clusters, or GPCs for short.
And then, if we zoom into each of those neighborhoods, each GPC, you'll find they're divided up into smaller blocks. These are called streaming multiprocessors, or SMs. This is where things start to get really busy.
And then we zoom in one more level. Inside every single one of those SMs, you find the real magic, the actual individual processor cores. Think of these as thousands and thousands of tiny little calculators, all ready to do the math. These are the real workhorses.
And these little calculators aren't all the same. They're specialists. You've got your CUDA cores, which are kind of the general-purpose grunts doing most of the graphics work. Then you have tensor cores, which are absolute wizards at the kind of math needed for AI. And finally, you've got the RT cores, which are built for one specific, incredibly complex job, figuring out how light bounces around a scene to create that stunningly realistic ray tracing. Okay, now for something that's actually super interesting about how these things are made. You'd think, right, that a really high-end card and a lower-end one would use totally different chips. But a lot of the time, they don't. They're actually the exact same piece of silicon. So how does that work? Well, making a perfect chip with billions of transistors is next to impossible. Tiny little flaws are almost inevitable. So instead of throwing away a chip that has a tiny defect, the manufacturers just turn off the broken part. Then they sort them into different piles, a process they call binning. The absolutely perfect chips become the top-tier cards. The ones with a few disabled cores, they get sold as the next model down. It's a super clever way to reduce waste.
Okay, so that's the hardware. Thousands upon thousands of tiny calculators. But how does the software actually use all of them at once? Let's get into the strategy here.
It all comes down to a concept with, honestly, the best name ever: embarrassingly parallel problems. This just means a huge problem that's really easy to break up into tons of smaller, identical problems. The key is that none of the little problems depend on each other, so you can have thousands of those cores work on them all at the exact same time. And guess what? Rendering graphics is the perfect, embarrassingly parallel problem.
The principle behind this is called SIMD, which stands for Single Instruction Multiple Data. Let's use an example. Say you have a 3D model of a cowboy hat, and it's made up of 14,000 individual points, or vertices. To move the hat, the GPU doesn't send 14,000 separate instructions. No way. It sends just one instruction, move this point, and 14,000 different cores all execute that same instruction on their own individual point, all at the same time. Boom! The entire hat moves instantly.
And this idea, doing one simple thing millions of times at once, that's the superpower. And it's why GPUs have become absolutely essential for way more than just making your games look pretty.
I mean, think about it. For video games, it's calculating the color of millions of pixels every frame. For something like Bitcoin mining, it's running the exact same math problem over and over, just with slightly different numbers, hoping to get lucky. And for artificial intelligence, it's doing the trillions of repetitive calculations needed to train those massive neural networks. They are all, at their core, embarrassingly parallel.
And this push for specialization gets even more extreme. You know, for a while, GPUs were the absolute kings of Bitcoin mining. But then, people developed even more specialized hardware, called ASICs. These things do literally one job and one job only, mine Bitcoin. And they are so good at it that, as this great quote says, they make a top-end graphics card look like a spoon trying to do the work of a giant excavator.
So that really is the main takeaway here. The magic of the GPU isn't that its little calculators are super fast. They're not, really. The magic is that there are thousands of them, all working together in perfect sync. It really is the ultimate computational cargo ship.
And that kind of leaves us with a pretty big question for the future. We know the demand for this kind of parallel processing is just exploding, mostly because of AI. So, based on everything we've talked about, specialization, architecture, what do you think comes next? How is the GPU going to evolve to keep up with these just unbelievable demands?